In this presentation, we discuss power as it relates to alternating current circuits, and we're going to define power in terms of the different components that we've looked at: resistance, capacitance, and inductance. So in general, we could talk about the power in a circuit, or the instantaneous power, and if we wanted to calculate the power, we would multiply the current times the voltage. So in this particular case, I have some load that is attached to some power supply over here that has alternating voltage, and that produces some alternating current that goes through that load. And so in general, the power is the voltage times the current, or the current times the voltage. But the issue is that when we have an AC source, and that load could be comprised of resistors, inductors, or capacitors, the current that's coming out of the source is not necessarily in phase with the voltage of the source. So over here we actually have a picture of what that might look like. So the solid line here is what the voltage might look like as a function of time, and then the dotted line represents the current as a function of time. And so in this particular picture, the voltage is leading the current by some phase angle that's associated with it. And so this load actually has a resistor in it, and also, let's see, if the voltage leads, then it also has an inductor that's dominating in this circuit. So if power is current times voltage, and we were to take at any instant in time and multiply those values together, we would get an expression for what the power would look like as a function of time. And so basically you can imagine at any given time here that you would have to add, or you'd have to multiply, these two quantities together. And so, here the voltage and the current are both positive values, basically until I get to this point right here. And so the power, the instantaneous power, is always going to be positive. But then we get to a point where the current is still a positive value in one direction, right? And the voltage is actually, the polarity is opposite. And so when you multiply the current times the voltage here, you actually get a negative value. And then, of course, when you have both negative voltage and negative current in terms of their direction and polarity, then if you multiply those together, you get a positive again, and then when they're opposite, you're going to get a negative. So the power, as it fluctuates in time, can be positive, right? Here it's positive. It can actually be zero, right? So there's an instant in time right here where the total power is zero, and it can also be negative. And so because the current and the voltage are not in phase, the power is going to have this fluctuation, and we're going to have to think about it in terms of power being positive or negative or zero. And so when the power is positive, we say that there is actually energy that's stored in the load. And when the power is negative, we say that the power is being released from the load. And we're going to talk about what those two terms actually mean. So what we're going to be interested in is the average power, because the power is fluctuating in time. We're going to want to determine what is the power over one cycle. And so we have to redefine our idea of power in terms of the different components, right? The resistors, capacitors, inductors, and basically the overall impedance in our circuit. So the very first thing that we're going to look at is the active power, the real power in the circuit. And the real power in the circuit is going to end up coming from a resistor that's in the circuit. And so the real power is always going to either be positive or zero. So on average, more power flows into the load than returns from it. And that means that you're going to have a positive value. So in our previous picture, the positive values for the power were always on average larger than the negative values. And those values are going to be, they're going to end up being the active powers that we're going to see. And then there's also situations, of course, where you could have zero power. And if you had zero power, then all the power that's sent to the load is actually returned back to the load. And that would be a situation where you only have an inductor or a capacitor component connected to the power supply. So let's look at those in a little bit more detail, starting with the resistor. Um, but let me just talk about, I guess, the reactive power first. So we've got real power. Real power comes from resistors. The resistors will dissipate heat, and they don't return that energy back to the load. They basically use the energy. On the other hand, you have reactive powers. And so during the times when the power at a particular instant in time is negative, that means that power is being returned from the load. It was stored in the capacitor, the inductor, and then it can be returned back again. So this is kind of like opening and closing a switch in DC. So you charge a capacitor, it's fully charged, and then you switch the switch so that it can discharge. It stores that energy, and then it can release that energy. So it's the same thing that's true for an AC source. So if that source is sort of charging up the capacitor, then you can have a situation where the capacitor discharges and provides that energy back to the source again. And so this is called reactive power, because it's something that over the cycle of over one cycle, the average of that is going to end up being zero, but we still have to account for it, and we'll see how that works out. So the average of that reactive power is always going to be zero. This only is true for inductors and capacitors, and so we're going to see that. So those are special, and so inductors and capacitors are those devices that can store energy and then release that energy. So when we talk about reactive power, it does those components that have reactive power, they actually cannot do any sort of useful amount of work in the circuit, so they don't produce heat. That's the resistor. But we still have to take it into account, because that reactive power still draws current from our circuit, and if we're not careful, we could have a component in there that's not making any or doing any useful work, but still having a big impact on the circuit. So let's start with just looking at each one of these components separately and looking at what the power is through those different components. So if I had an AC source and I had a resistor that was connected to that source, I could calculate what the power is through that resistor. So the power as a function of time would be the current or the voltage multiplied by the current. And we know that when we have just a resistor in the circuit, that the current and the voltage are in phase with one another. So we're just saying that in this case, the source has an amplitude voltage of V and a phase angle of 0, and then the current would have some amplitude associated with it with the same phase angle of 0. So I could write this as combining those two sine terms and writing it as sine squared, and then I would pull out the amplitudes of the voltage and the current that are coming, the voltage of the source and then the current that's produced from being connected to that resistor. Now, I'm always interested in not the instantaneous power, but the power over one cycle, so I'd like to calculate the average of this over one cycle. So if I use one of the trig identities that I know, that sine squared is equal to 1/2, that's where this 2 comes from, 1 minus cosine of twice the angle, then I could calculate the average of this function, which is the power as a function of time, and I could calculate what the average is. Now, in previous lectures, we looked at what the average power was over one cycle, and we went through all this, so I'm not going to do it again, but one of the things that we should realize is that when we take the average of a sine function or a cosine function over one cycle, we always get 0. And so if I average, and this is actually cosine of twice the angle, so if I average this over one cycle, this cosine term is going to be 0, but I still have that 1 out front. So the average power over one cycle is just going to be equal to this first term right here, where that cosine term goes away when I average it over that one cycle. So this is something that we saw before, and so the average power for a resistor connected in a circuit is just going to be the current that's going through the resistor, the voltage that is going across the resistor, the amplitude over 2. And this is actually where we defined the effective values, or the RMS values. So if I separate out that 2 with the square root of 2 and the square root of 2, then I have the amplitude of the current over the square root of 2, the amplitude of the voltage over the square root of 2, and this is just the RMS values. So this is a way that we can relate power in an AC circuit to power in DC if we compare their RMS values, right? So power in DC was current times voltage, and here we have the average power in an AC circuit is the RMS value of the current times the RMS value of the voltage. So we write these RMS values as just current times voltage, just so we sort of have this comparison to DC. So if we go through that same process and we use the equivalent of Ohm's law, we can write the power as current times voltage, current squared times resistance, or voltage squared over resistance, just applying Ohm's law to that. So again, these are things that we've seen before, and I wanted to make sure that everybody keeps in mind that the current and the voltage here are the RMS values when we're talking about the power, and this is the average power over one cycle for a resistor. All right, let's consider an inductor. So with an inductor, what we know about an inductor that's connected to an AC source is that the voltage across the inductor leads the current through the inductor by 90 degrees. And so if I were to make a plot of these, as has been done down here, I have the voltage starts off as a maximum, and then I have over one cycle here, it goes through its cycle, and then the current is shifted by 90 degrees. So here's my current, the dotted line here. And one of the things that you should notice when you look at this is that, we've got positive power over part of the cycle, negative power, and then positive power and negative power. And so if we look at this carefully, we realize that we have stored energy, released energy, stored energy, released energy, and over one complete cycle, the amount of positive power we have is the same as the negative power, so the average is going to end up being 0. Or if you calculate the area under the power curve, that's going to end up being a 0 value. So if we look at this a little more carefully, we can write down that the power is the voltage times the current, where the voltage leads the current. I can pull out the amplitudes, and I can write this as sine with a phase angle of 90 times sine with a phase angle of 0. I can use one of my trig identities, and I can write down sine omega t plus 90 times sine omega t is just equal to 1/2 cosine, excuse me, 1/2 of sine of twice the angle. So sine omega t plus 90 times sine omega t in terms of the trig identities is 1/2 sine of 2 omega t. Well, over one cycle, well, first of all, I guess I should say here is that I can write these, the voltage of the amplitude of each of the voltage and the current over 2. I can separate out this 2 as the square root of 2 times the square root of 2, and I can write those as the effective values or the RMS values. And then if I were to average this over one cycle, the average of a sine function, or twice the angle here of one cycle, the average power is going to be 0. So the average power for an inductor connected to an AC source is always going to be 0. So I realized this was on the screen earlier, but I didn't want to stop. So we're going to define something called reactive power. And reactive power is defined the same way as average power. So it is the voltage times the current, right? It's the term that's out front here, voltage times current, which is where we started. But it's not going to contribute anything to the average real power. Because of that, and I didn't mention the units earlier for power. So in general, power units that we have been using are watts, right? So power is joules per second, which is a watt. When we talk about reactive power, it's still voltage times current. So in reality, it's still going to give us the it's still going to give us watts in general. But in order to specify that this is reactive power and not real power from a resistor, we use separate units, and we use units that are VAR. And so you might wonder, where does that come from? The V comes from the volts, the A comes from the amps of current, and the R comes from the fact that it's a reactive component. So we have power for resistors, that's going to be in watts, and reactive power is going to be in these VAR units. If you have an inductor, the reactive power is taken to be a positive value. And so we can write the reactive power using the equivalent of Ohm's law for DC, for AC, excuse me, the equivalent of Ohm's law for AC. And we know that for an inductor, the voltage is equal to the current times the inductive reactance. So if I replace the voltage here with the current times the inductive reactance, I get current squared times inductive reactance. And then if I were to instead replace the current with the voltage divided by the inductive reactance, I would get the same term right here. So this looks very similar to the real power for a resistor. The big difference here is instead of resistance, I have inductive reactance. And it's also a different type of power. If I go through the same process for a capacitor that's connected to an AC source, the big difference here, of course, with the capacitor is that the current leads the voltage by 90 degrees. So this has a negative phase angle. So that means that the current is actually ahead of the voltage. And we can see that here. The current is a maximum first, and then the voltage is a maximum later. If I go through the same process and I look at multiplying these two quantities together, I realize that there is energy that's released, and then energy that's stored, and then energy that's released, and then energy that's stored. But over one cycle, if you take the average of the power under the curve, you're going to have the same amount of positive as negative, and so they're going to cancel out, and you're going to get an average power of 0. So if I were to go through the same process, I could write down power is voltage times current. I can pull out the amplitude of the voltage and the current out front, and I have these two sine functions. If I use one of the trig identities, I realize that sine omega t minus 90 times sine omega t is negative 1/2 sine of 2 omega t. This 2 can be broken up into the square root of 2 and the square root of 2, and I can write these amplitudes in terms of their RMS values. There's a negative sign out front, and I realize that if I average this power across the capacitor over one cycle, that the average of the sine function is going to be 0. So again, if we're talking about the reactive power for a capacitor, the average is going to be 0, but we still can take into account the fact that there is this reactive power in the circuit, and we define the reactive power as the voltage times the current, just as we did before, where this is the voltage across the capacitor and the current through the capacitor. Again, it contributes nothing to the average real power, so over one cycle it's going to be 0, but we still have to define this power in our circuit. It has the same units, VAR, as inductive reactive power. But the only thing that's different here is that now if we have a capacitor, we take this reactive power to be negative, so that it has a different impact on the circuit compared to the inductor. And then, of course, using the same reasoning as before for AC sources, if you have a capacitor connected to an AC source, we can use the equivalent of Ohm's law. We could write down the voltage is equal to the current times the capacitive reactance, and if we substitute that in here, we get I squared times the capacitive reactance, and then the same reasoning, we get that other expression. So this also looks like the average power where we've replaced resistance with capacitive reactance. All right, so let's see if we can look at an example of this. So we have a circuit, and in this circuit I have one resistor, I have two capacitors, and I have an inductor, and it's connected to some source over here, and I know that I have 20 amps entering and then I have 200 volts across the two parallel components. So obviously these are actually AC sources, and what they're giving us here, this 20 and this 200, are going to be our effective values or RMS values. We're going to assume that. I haven't given you any reason to not say that those are the values, but the currents is fluctuating in time and the voltage is fluctuating in time, but these are just going to be our effective values. So I want to figure out what is the total power in the circuit and what is the total reactive power in the circuit. So real power, which I'll just say power, and then the reactive power. So to find the real power in the circuit, I can take the current squared times the resistance. I know that the current is 20 amps, the resistance is 3 ohms. 20 squared times 3 ohms gives me 1,200 watts. In order to find the total reactive power, I have to find the reactive power for each of the different components. So I can find the reactive power for capacitor 1. I know it has a capacitive reactance of 6 ohms, and I know the current is 20 amps. So I have 20 amps squared times 6, and that is 2,400, and the different units here, right, are going to be VAR units. And then I haven't put the fact that it's negative in. What I've done is I've put in parentheses capac or cap. This means that this type of reactive power is capacitive. I have another capacitor here, which has a capacitive reactance of 10 ohms, and it has a voltage of 200 volts because it's connected in parallel to the inductor. So 200 volts squared over 10 gives me 4,000 VAR, and then again in parentheses, this is from a capacitor. Finally, I can calculate the reactance for the inductor here, and so that's going to be the voltage squared over the inductive reactance. And so this is going to be 200 squared over 5, so that's going to give me 8,000 VAR, and then in parentheses, this is inductive. So my goal was to calculate the total power and the total reactive power. And so to calculate the total reactive power, I have to add all of these reactive powers for each of the components in the circuit. This is very similar to if you had resistors in a series parallel network. You could calculate the power for each of those resistors and then add them together. So I'm going to do the same thing here for the reactive power, but I'm going to take into account the fact that capacitive reactive power is negative, inductive reactive power is positive. So now the fact that I put cap next to these two and inductive next to the last one is going to be important. So the total reactive power is negative 2,400 VAR, plus a negative 4,000 VAR, plus positive 8,000 VAR. And so I end up with, when I add all these together, I get 1,600 VAR. It turns out to be positive, which means that it has that the inductive part of this reactive power dominates in total, and then the total real power in the circuit is 1,200 watts. So we've looked at each of the components individually, and we've calculated the total power, and we've calculated the total reactive power. The other part of this question says reduce the circuit to its simplest form. And after we reduce it to its simplest form, then we could actually calculate the total power. So let's go ahead and do that as well. So I have still down here, what I found previously, and I'm going to leave that there. So the first thing I realize is that I have an inductor, and I have a capacitor, and they are connected in parallel, so I can combine those together into some total equivalent impedance. And since they are in parallel and there's only two of them, I can write the total equivalent impedance as the impedance of the capacitor times the inductor over the addition of those two values together. The capacitor has a capacitive reactance of 10 ohms, and of course it's a capacitor, so it has, for its impedance, has a phase angle of -90. The inductor has an inductive reactance of 5 ohms, and because it's an inductor, it has a phase angle of 90. And then I can add those two impedance values together. The capacitor is negative, and the inductor is positive. So if I subtract the two quantities at the bottom, I get a negative 5 ohm imaginary piece. Multiplying the two terms at the top, 10 times 5 is 50. When I get the phase angle here, it ends up being 0. I can write the bottom term in its polar form, and it looks like I have a 5 ohm reactive capacitive reactance term because of this negative. And so when I solve for the total impedance, 50 divided by 5 is 10, and then when I subtract the angles here, I get 90. And of course, this means that the total equivalent impedance of these two components connected together is basically equivalent to a single inductor that has an inductive reactance of 10 ohms. So once I have combined those two together, I can look at my circuit again, and I realize that it's equivalent to 3 impedance values connected together in series. So here's my resistor, which I've written in its impedance form. And then here is my first capacitor, which was 6 ohms, and then I've written it again as a negative 90. And then I can put my total equivalent impedance for those two components together. Because they are all in series, I can add them all together. So I can calculate the total impedance in the circuit. And so I have my resistive piece, I have my capacitive piece, and then I have my total equivalent of those two components together, which ends up being just impedance. And so when I add them together, the resistive piece in my circuit is 3 ohms, and the reactive components gives me a total value of 4 ohms. So I can replace all 3 of these impedance values with a single impedance that's equivalent to one resistor that is 3 ohms and one inductor that has an inductive reactance of 4 ohms. So using these values, I can calculate the total power in the circuit by looking at the total impedance. And so the resistive piece gives me a real power of the current squared times the resistance. The current that's entering these 3 pieces that are connected in series, equivalent to this impedance, is 20 squared times 3, which gives me 1,200 watts. And then I can find the reactive power, current squared times the inductive reactance. And so this would be 20 amps squared, and then the reactive piece is 4 ohms. And so when I multiply that, I get 1,600 VAR, and I know that it's inductive because the total impedance is equivalent to an inductive piece. So regardless of whether I look at the individual components and I calculate the total power and the total reactive power, I get the same value as if I reduce the circuit down to a single impedance, where from that single impedance I can assume I have a single resistor and a single reactive component, and in this particular case it happens to be inductive because this turned out to be positive.